So let us try to understand, first of all, what happens in a wireless channel and how the phenomena that are taking place in wireless channel are posing challenges in transmitting bits at a very high rate. So let us first try to understand wireless channel. So as we have discussed earlier, if we consider the medium to be only noisy, that is additive white Gaussian noise, then the performance of the system is at one level. But a wireless medium is much more than that. It is not only noisy but also a fading channel, which means what? Let us try to understand. Traditionally, as we pointed out earlier, there used to be wireless communication from when the transmitter and receiver are placed on hilltops, and there is a line of sight communication, and the distance between transmitter and receiver is very large, and therefore the communication was easy using free space medium, and there can be also ground wave reflection. In spite of that, the communication can be easily obtained. The wireless medium is not a big hindrance. The wireless medium itself is modeled into two types. One is a large scale phenomenon and the small scale phenomenon. So the large scale phenomenon means the distance between the transmitter and receiver is very large, and the antennas will be on hilltops, and therefore only direct path and small one or two reflected paths are available. And the range of such wireless communication is normally decided based on the average signal power that is received at the destination. So that is how range is fixed, and it was happily going on. But when we think of a wireless communication, wireless mobile communication particularly, we know that the mobile devices are moving on the ground. Mobile devices, when the signal has to reach the mobile devices, the transmitted signal will face a lot of obstacles in the path. So these obstacles are going to cause severe degradation in the performance of the system. So let us see what they will do. First of all, let us try to understand what we expect at the receiver when we transmit a particular signal. So if I think of a pulse waveform, okay, if you send one pulse, maybe representing one particular bit, one bit 1 or bit 0, through a channel, it goes through a channel. At the end of the channel, we require this, we expect this pulse to come out as it is. But unfortunately, now if this pulse has to come out as it is through the channel bandwidth has to be infinite, because this pulse instantaneously rises and instantaneously falls. That means very high speed or very high frequency component is present in this waveform. Similarly, instantaneously it falls down. So very high frequency is present in this particular waveform, apart from low frequencies. So if this waveform has to come out as it is through a channel, the channel has to have infinite bandwidth. But unfortunately, all practical channels, whether it is a wired or wireless, they all have finite bandwidth. And because of that finite nature, so finite bandwidth, all channels are finite bandwidth channels. And because of that finite bandwidth nature, what happens is the waveform, instead of getting received like this, it will be something like this. Okay, so there will be a dispersion like this, because instantaneously input rises to this value, whereas the channel cannot respond at that speed. It could respond only at this rate, and therefore slowly the output rises, and it is in this region. This region, and then instantaneously input falls, whereas channel is not able to instantaneously input it to 0. It is allowing it to fall slowly, and this is what is going to happen in a practical channel. Now, how people have handled this kind of effect in the channel? This happens in wireless medium as well as in wired medium. So basically, this was representing one particular bit, 1, and a 0 could have been here. Let us say 0 is here. So you would expect it like this. Okay. So the effect of this particular phenomenon is that this bit that is received here is interfering with the neighboring bit. Neighboring bit is transmitted during this period. During this period, you transmit another bit, but unfortunately, the effect of the previous bit is also present in the next bit, and this is called ISI, inter-symbol interference. Inter-symbol interference is going to take place. So this inter-symbol interference has to be either can be tolerated or has to be removed. So if you want to remove this, you require some complex signal processing, particularly what is known as equalizer is used in order to remove this remove the effect of this inter-symbol interference. Okay, so ISI is removed using what is known as equalizer. Now, without using an equalizer, if you still want to communicate through a band limiter channel, what can we do? What people have done is, suppose this is the level of interference, and this is the rise time and then the fall time. Now, if you look at the waveform, if one waveform, if you transmit like this, so if the pulse duration is this, here the pulse duration is, in other words, so this is, let us say, T1, this is T2. So bit rate is 1 by T1, and this is bit rate is equal to 1 by T2. So this bit that you transmitted was received like this. This bit that you transmitted was received like this. Now, in this case, the interference or the inter-symbol interference exists for some time during the, only for not existing for a major portion of the bit duration, whereas this interference exists for a major portion, more than 50% of the next bit. This is interfering, whereas it is interfering only maybe 10% of the bit. The remaining bit duration is interference free. So, what people have done is, in order to detect the original bit which is transmitted, you can sample at the midpoint of the every bit, and then based on this midpoint value, you make a decision. In the midpoint, you have a correct bit. There is no interference here. Whereas here, at the midpoint, there is an inter-symbol interference, and this is going to cause some error. Whereas this kind of interference is not going to cause any error if you make a midpoint sampling. Or if you use a matcher filter for detecting the bit, then also the interference here will be very low compared to the interference that is being faced. Of course, match filter is optimum only against noise. So the bit rates are chosen in such a way that this interference is less than 10% of the bit duration. So it goes now. This goes 50% of the bit duration. This goes only 10% of the bit duration. So you select this bit duration accordingly. That means you select the bit rate. So given a bandwidth, the bit rate, maximum bit rate that you can transmit will depend upon the intersymbol difference. Depend upon this bandwidth. So depend upon the fall time or rise time. Okay. So this is what is going to happen. This, apart from the noise is also getting added. Now this waveform will be received as a noisy waveform. Without noise, I have just shown you. Now, if noise also is added, the noisy waveform look like this. So it will be available like that. So apart from the interference, intersymbol difference, noise also is getting added, and therefore the performance degradation will take place. Okay, this is simple, finiteness of the bandwidth of the channel, and this is the kind of effect that it is going to cause. Without equalizer, you can manage if you can choose the bit rate in such a way that it is allowing only 10% of the allowing the intersymbol difference only 10% of the bit duration. So in other words, the bit rate has to be reduced in order to handle this kind of an interference, intersymbol interference. But bandwidth is very expensive, and you would like to transmit as much data at as much speed as possible with a given bandwidth. So normally, one would like to, the bandwidth efficiency should be as high as possible. Bandwidth efficiency means bits per symbol RB by say B. So many bits per second per hertz of the bandwidth. So per hertz of the bandwidth that you spend, the bits per second that you want to transmit should be as high as possible. Okay, this can be 1, 2, 3, 4 people are trying to achieve 10. Okay, so that means bit rate and bandwidth are not the same. If you have 1 hertz of the bandwidth, whether you can transmit 1 bit per second or 2 bits per second or 10 bits per second, it will all depend upon the kind of signaling scheme, the count of signal processing functions that you incorporate in the system. So one would like this value to be as high as possible. Okay? Of course, Shannon has given a limit of maximum rate that you can transmit through a channel and a signal to noise ratio. So given a bandwidth, we would like to transmit at as high a speed as possible, but just because there is going to be an intersymbol interference, if you reduce the bit rate, then we are unnecessarily spending this bandwidth, which is a very costly proportion. Therefore, how to transmit at high speed, even in presence of intersymbol interference? So people use equalizer at the receiver. Equalizer will undo what the channel has done. So if channel has introduced this one, equalizer will do the opposite. So how does the equalizer know that channel has done this? So certain measurements have to be done across the channel, and these effects of the channel is given to the receiver, and the equalizer is trained accordingly. So it's a tap delay and filter. The coefficients will be set according to the kind of interference that one experiences. So system will become more and more complicated, but then we don't mind making this complicated because we want to save the bandwidth. The given bandwidth we would like to transmit at very high speed. Okay, this is one very straightforward effect that we will have in wired channel as well as in wireless channel. But in wireless channel, even much more severe degradation will take place. Let us try to understand what are they. So this is true in every channel. So we will not go into the effect of noise now, because ultimately in the channel there is going to be a noise, there is going to be this kind of interference, and there is going to be fading, signal strength will increase, decrease and so on. But the fading effect is much more predominant compared to the effect of noise. So always people will deal with the fading phenomenon with a lot of seriousness than this noise. Only thing is, noise will reduce the immunity of the receiver, and how it will appear we will see later. So let us see how wireless channel there is a phenomenon called multipath reception. What does it mean? So you have a transmitter and you have a receiver. The receiver could be mobile, okay? Receiver, mobile receiver. Let's say mobile receiver. Transmitter also can be a mobile, but it goes to the base station and comes. This is a, let us say, a base station. So mobile. So it is an environment in which the receiver is moving. And there can be a direct signal available here. There can be some building here, okay? Some building here, whatever it is. And there can be a tree here, something. So there can be some structures there, tall structures, something like this. So there will be signal reflected and comes here, goes there, and then again goes there, and then comes here. So these kind of lot of reflected signals will reach this. This is called multipath reception. There is one direct path and there are multiple paths. This will happen because on the terrain there is a receiver, mobile receiver is moving or not moving, but from the base station signal enters into the terrain, and while entering it may find one direct path, may find, may not find, but it will find also a lot of multiple paths, and same signal will go through this, through that, through that, through that. So then what happens? What is the effect? This is going to cause a serious degradation in the reception process. So what will happen? In order to understand this phenomenon, we need to consider as if we are transmitting one impulse. That means we are transmitting this signal, impulse. At time t is equal to 0, okay, t equal to 0, t equal to 0, we transmit this impulse, whatever value it is. So it has to reach directly at the receiver. What you will receive, this is the transmitter, and at the receiver, mobile receiver, you will get the direct path. Okay, the direct path may. Now the question is, it travels a distance. This also travels a distance. This also travels a distance. Everything travels a distance. Now the signal can get reflected from a particular structure, or there can be a diffraction from the structure is irregular, there can be a diffraction, and there are small objects which are of the order of wavelength of the signal, then there will be scattering. So all kinds of phenomena can take place and then they reach here. So whatever is the, say, value that you, let us call this as say some 1. Okay, 1. You transmit 1. But what you receive in a direct path, you may not receive 1. You may receive, let us say, you may receive 0.7. Okay? This 1 will come, value of the 0.7 will come, let us say. And these values, this will come later. With some delay, some other. What is the delay? Now the question is, many different paths are available and the delay will also be different. So I will just show you with a fixed delay. Okay, every path is a fixed delay because between the one value t is equal to say t tau, I call it tau 0. Now another path may come like this. Third path may be like this. Okay, and then fourth path like this, like that. So a different, so tau 1, tau 2, tau 3, tau 4. Same, we transmitted only one impulse. That impulse was directly received here at the same time. Let us say there is, I consider this propagation to be very small, let us say, and the multipath another value, one other path a different value, another path like the multiple path. The effect of this impulse that you transmit at this time lingers up to this time. You transmit only one impulse, but what you receive is so many impulses. This is the impulse response of this channel. That means there is going to be a, then there may be there, so it will stop. Okay, this is impulse. That means what? Whatever you transmitted at this instant, we will see its effect up to, let us say, 5 tau. This tau, this is the average delay, multipath delay. How to find out this average delay, etc. We will see. What is the effect of this average delay? We will see. RMS delay, average delay, and so on. So these impulses are available. So what will happen now if you are transmitting one impulse here and then you transmit another impulse here, let us say. Second impulse you are transmitting here. So at this time you have the effect of this one, okay, and it will get added, or we do not know whether it is constructively getting added. The impulse will get added, let us say, positive. But if it is a sine wave, then of course we don't transmit impulses across the wireless channel. I am only making you feel what a signal will experience when it encounters multipath channel. So if you transmit an impulse, you will get a result like this. And if you transmit another impulse at this time, it is not that same pattern will repeat here. Now this impulse done. Now you may consider the channel as a system. You consider it as a system. Normally, it is very easy for us to assume every system to be linearly, system to be LTI, linear time invariant system, and then easy to analyze. So we expect a linearity across the channel, both amplitude and phase linearity. But what is time invariant? You transmitted one impulse here, you got an effect like this. You transmit another impulse here, the effect will not be like this. The effect may be different because when you transmit another impulse, at that time, the receiver would have moved, or the obstacles could be moving or maybe fixed. So a different type of environment will be present between the transmitter and the receiver. The receiver would have moved from here to here, for example. So the whole environment has to change for the transmitter to the receiver. So the multiple paths will experience different amplitudes, different attenuations. So you won't get, for this impulse you got this pattern. For another impulse you transmit later, you won't get this pattern, you will get a different impulse response. So, every time you transmit an impulse, the response will be different type. So, it is not a time invariant, it is a time variant phenomenon. Very complicated. So, if it is a time invariant phenomenon, you know that this is what is going to happen in this channel, so you can easily correct it. But if it is going to be a time varying phenomenon, then it is very difficult for us to correct that phenomenon. So people have done, introduced certain techniques in order to adaptively monitor this time varying phenomenon and correct the effect. So multipath will cause time varying responses at the receiver. And now this is the impulse. Now let us see, but we don't transmit impulses, we transmit sine waves. Okay? Now I will show you with respect to sine wave. Sine wave means what we normally have a data with some rate like this. Okay? And then we modulated waveform will be something like this. Let us say this is frequency modulation. So there will be one frequency here, another frequency there, and like that it goes. If it is a phase modulation, ESK phase modulation, then what is something like that. There is a phase change here, whereas here there is a frequency change. In frequency modulation, you would get this type of waveform. In phase modulation, you would find this type of waveform. This is the waveform that you will convert to electromagnetic radiation, and it will be sent across the medium. At the receiver, there is an antenna, so transmitting and receiving antenna. Antenna will give you the electrical signal out, and that electrical signal is what we are dealing with. We are not talking about RF. So this is what is the signal that you transmit. At the receiver, this sine wave, you are expecting the sine wave to come to the receiver during this time duration, because in this time duration this waveform represents this bit, this waveform represents that bit. Similarly, this waveform represents this bit, this waveform represents that bit. So we expect this waveform to come during this time duration only. Unfortunately, because of the multipath, this waveform will not only come directly here, and it also a delayed version of the same waveform also is received because of the multiple path, and that delayed version will go and affect the next bit. And how does it affect? If a sine wave is like this, and I expect that sine wave like this, but I also receive a delayed sine wave like this. Okay? So what happens at this time instant? I expected sine wave like this, but I receive this. I also receive another wave like that. The amplitude may be different. Okay? So at this time, what is the value I get? I get this value, I get that value, I get that value. So what I expected was this sine wave. I get this, I get this, I add this. So this is negative, this is 0. So this is positive I expect, but one negative is getting added, and therefore this total resultant value will be less than this value. Okay? Sometimes, suppose here, for example, at this point, you get this, you get this, you get this. So all this you add, all of them are positive. So you get a better value. So you expected a positive value like this, but I get a much better signal strength. So here I expected this signal strength at the receiver, but because of the multi-path, what has happened is I receive less than this value because there is a negative which is getting, this is called what is that? The signal can get constructively added or destructively added. This is destructive addition. That means you positive got, but unfortunately you got a negative also to reduce the signal strength. Whereas here you expected this much value, but unfortunately this and this are getting added, so better signal you will receive. So sometimes you will receive a inferior signal. You transmit one, say 1 volt. Sometimes you will receive 0.3 volt. Sometimes you receive 1.3 volt or 1.5 volt, depending upon how much is the delay and how many such delayed waveforms are reaching the receiver. Now I add all this, the resultant only will be received at the receiver. This one, that one, all of them getting added. The resultant waveform is this one. So I transmitted one sine wave like this during this period. I expected this waveform to reach my receiver, but unfortunately I received one other waveform which may not be a sine wave, which may be something like this. Let us say some waveform like this, which will extend like this also, because the multipath is going, the effect is going. So I transmitted one sine wave, I received this type of waveform. If it is same sine wave received in this period, I know how to get back this. From this, if you demodulate, I will get this. I know what is the process of getting back this. But instead of getting this, I get this type of waveform, which is not a sine wave exactly which what I transmitted, but there is something different. So this is going to be the effect. If it is within this period, there is one aspect. But it extends to the next also. So it is going to cause intersymbol difference. This signal that goes from this duration to that duration is going to cause intersymbol difference at the end of the receiver. So what happens in the channel is happening on the sine wave. The impulse response, we are not transmitting an impulse response. We can think of the sine wave as many impulses. So one impulse here, another impulse here, another impulse. So you are transmitting one impulse here. The response of that impulse will be all that. We shown this, you add them. So similarly, the response of this impulse will be different. So at this particular time, whatever is the response